In this lecture, we'll be talking about mass balance problems in which we have combustion reactions. These reactions most commonly are reactions of a hydrocarbon fuel with oxygen. Hydrocarbons consist primarily of carbon and hydrogen, and when a carbon atom reacts from a hydrocarbon molecule with oxygen, we generally think of it reacting to form CO2. However, we can have a carbon atom react with oxygen to produce CO according to the second reaction that you see here. When we have CO formation, we refer to the combustion process as being partial or incomplete. In all cases, we're going to assume that when we have hydrogen in a hydrocarbon and it's in a combustion reaction reacting with oxygen, it forms water according to this reaction right here. And sometimes we'll have sulfur. Sulfur is a common contaminant in fuels. And when sulfur reacts with oxygen, it will form SO2 according to the very last reaction that you see there. Combustion reactions are a reaction with oxygen. This oxygen typically is supplied by simply supplying air, not in a purified form. And for the purposes of the problems we'll be working here, we're going to assume that air is 79% nitrogen and 21% oxygen. Now we know air is not exactly this, that it contains a little bit of argon, up to approximately 1%, and there's other gases. But for the purposes of the calculations we'll do here, we're going to assume that air consists of 79% nitrogen and 21% oxygen. Of course, with combustion reactions, we're going to have a whole set of new terminology to deal with, and those terms are summarized here. The first and probably most important one is that we'll make a distinction between whether compositions are specified on a wet basis or a dry basis. The difference is stated here. When compositions are specified on a wet basis, that means the mole fractions have been calculated, including water in the calculation. When mole fractions are specified on a dry basis, that means that water was not included in the calculation. And we're going to see an example of this in the very first problem that we work. Theoretical air really builds upon the description of theoretical amounts that we've talked about in previous reactions with problems involving reactors. The theoretical air is the quantity of air that contains the quantity of oxygen that's required for complete combustion of all of the fuel. So theoretical air includes not just the quantity of oxygen required, the theoretical quantity of oxygen required for complete combustion or complete reaction, but it also includes nitrogen that would come along with it. Now, excess air, which is also equal to the excess oxygen, is calculated by taking the air fed minus the theoretical amount of air that's required, dividing that difference by the theoretical amount that's required, and multiplying by 100. This is the exact same definition we've used for excess in the past. Here, if we put the air fed, or use air in this calculation, we get the percent excess air, but we'd get exactly the same percent excess if we just put in the amount of oxygen that was in the air and did this calculation. I'm not going to go through the proof of that, but if you like, you could probably go through that very easily by simply realizing that air is 21% oxygen. So if we multiply top and bottom of this fraction right here by 0.21, we get the amount of oxygen that's fed and the amount of oxygen theoretical. And for these problems, as with most of the reactor problems we've worked, we're going to use atomic balances. So this very first problem we're going to work is one in which we have N-pentane. N-pentane is a 5-carbon hydrocarbon, C5H12. It's burned with excess air. So that means that we have more than the theoretical amount of air present. We're told that the product gas contains 0.304 mole percent of pentane. So almost all the pentane has reacted. It has 10.2% CO2, both on a dry basis. So those compositions have been calculated without including water in the composition calculation. What I'd like for you to do now is to assume complete combustion in this process. So we're not going to be forming carbon monoxide. All the carbon reacts to form CO2. Then I want you to balance the chemical reaction and then draw and label a process flow diagram with the information that you're given here. You're probably going to find that there's a lot of unknowns, and you may find it difficult to include some of the information that you're given, some of the composition information, but go ahead and label it to the best of your ability. If you don't know how to include a piece of information, simply leave an unknown when you label the process streams, but make note of the fact that you have this additional piece of information, this additional piece of composition information. So I recommend that you now pause the presentation and spend a few minutes drawing and labeling the process flow diagram to the best of your ability, and then balancing the combustion reaction here. Balancing the reaction of pentane with oxygen to form CO2 and water. So take a moment now to do that. Well, I hope you took a moment to do that. And here's what I would draw. What's shown in the middle of this diagram is the combustor. And inside the combustor is a chemical reaction. We have pentane reacting with oxygen to form CO2 and water. Now, the coefficients here, I believe, make this chemical reaction balanced. So let's look at carbon to begin with. We have 5 carbons in this hydrocarbon. And over here on the right, we have 5 CO2s. We have 5 carbon atoms as well. Now, if we look at simply the hydrogen, all this hydrogen will end up in water. So we have 12 hydrogens here. We'd have to put 6 water molecules over here to account for all 12 hydrogen atoms. And finally, if we want the oxygen to balance, we realize that we have 5 CO2 molecules that are produced. There's 10 oxygen atoms that are needed for that, plus an additional 6 oxygen atoms in the water. So 10 plus 6 is 16. We need 8 oxygens in order to account for all the oxygen over here in the products. So the reaction is balanced. Now let's label the streams that come in. I'll label the 2 streams that come in. One is our hydrocarbon fuel. It's pure pentane, so the mole fraction of pentane is 1. And we don't know its flow rate yet. We also have some amount of air. We don't know its flow rate, so it's labeled as N2. And we know the composition of air is 21% oxygen and 79% nitrogen. Let's look over here at the product stream. The product stream, we don't know its flow rate. And I've listed all the compositions here, although later we're going to add in the molar flow rates as well. But instead of trying to calculate any of these compositions, I've listed them all as unknown. And the unknown composition, we have an unknown composition for pentane, oxygen, nitrogen, and CO2. And the water composition we're going to calculate by taking 1 minus all the other compositions. Now we do know the composition of pentane, and we do know the composition of CO2 on a dry basis. However, as written here, we've included water. So these compositions are on a wet basis. In the next slide, we're going to talk about how we can modify this drawing, this process flow diagram, to separate out the water, to have a hypothetical water stream, which will make some of the work a little bit easier. We're going to do that a little bit later. We're not going to worry about that right now. What I'd like to do is do a degree of freedom analysis on this problem right here. And so if we do an atomic balance, what I'd like to do is take a moment and then count the number of unknowns, count the number of atoms, count the number of inerts, and count the number of additional specifications that have been provided to determine what is the number of degrees of freedom that are left. I want you to take a moment right now and do that. Well, I hope you took a moment in order to do the degree of freedom analysis here, and let's review that. Now, when we do the degree of freedom analysis, it doesn't matter whether we do it with the streams labeled with an amount above and mole fractions below, or if we do the degree of freedom analysis with the component flow rates below. We end up with the same result. And I think we've worked a problem like that in the past, and if you want to, you can go back to one of the previous lectures and examine that. But we're going to do the degree of freedom analysis here simply using the composition information shown. So if you look around these streams, let's count the number of unknowns. So if you look at the 2 feed streams, we don't know the flow rate of our pentane feeds. That's one of the unknown. So there's 1 N associated with that. Nor do we know the flow rate of our oxygen. There's a second unknown. And if we look at flow rates, just flow rates, let's look at the flow rate of the product stream. We don't know it. So there's 3 unknown flow rates. So down here in the list of unknowns, I've listed 3 N values are unknown. Now let's count the number of unknown mole fractions. We know the mole fraction of both of the feeds here. We have pure pentane and we have air. Over here, for the product stream, we don't know any of the flows. We don't know any of the flows, therefore there are 4 unknown mole fractions, 4 X's. So the total, we have 3 unknown flows, 4 unknown mole fractions, so we have a total of 7 unknowns here. Next, in doing our degree of freedom analysis, we need to count the number of atoms. And the number of atoms we can calculate just by looking at the atoms that are present in each of the molecules that participate in this reaction. So if we look at these atoms here, we see there's, in the pentane, we have carbon and hydrogen. Those are 2 atoms that are listed down here. And we also have oxygen, which is listed down here as well. So there are 3 atoms that are present that participate in this reaction, 3 different atomic species. Let's count the number of inerts. The number of inerts is just 1. We have nitrogen. It does not participate in the reaction. And we can write an independent molecular species balance for it. So we have a -1 for that inert being present. And we do have those 2 additional specs that I mentioned. We have a composition of pentane and a composition of CO2 that have been given. So given this analysis, we take the number of unknowns, subtract off the number of atoms, and the number of inerts, and the number of specs that we have. We end up with 1 extra degree of freedom, which we're going to take care of, we're going to provide by assuming that we have 100 moles per hour of the dry gas coming out. And at this time, we're going to modify our process flow diagram to separate this product gas stream into 2 streams. We're going to separate into a water-only stream and a dry gas stream. We're going to see that on the next slide. Now what's shown here is the product stream split into 2 streams. The first, which is stream 3, is a stream that contains only the water that's produced by the combustion reaction. As you can see here, the mole fraction of water is indicated as being 1. And the second stream is the rest of the combustion product, the dry gas. As you can see here, we've assumed that we have 100 for the flow rate of this dry gas stream, and below is listed all the composition information that we had before. What we're going to do is take all this composition information and the flow rates that are indicated here and use this to determine each of the component flow rates in the streams that's present in this process. So let's first off start over here with the pentane feed. If we look at the pentane feed, the flow rate of this stream is N1, and we know the mole fraction of pentane is 1 here, so the flow rate of pentane in this stream is just equal to N1. If we look at the air feed that provides the oxygen for the combustion reaction, its flow rate is N2. We know that 21% of this is oxygen, so the flow rate of oxygen is 0.21 times N2. And likewise, the flow rate of nitrogen is given by the mole fraction of nitrogen, 0.79 times the total flow rate of this air stream, which is N2. The flow rate of water coming out in the stream over here is just going to be equal to N3. The total flow rate is N3, and it's all water. And we can calculate the flow rate of each of the other components in this dry gas product stream by simply taking the mole fraction and multiplying it by the total flow rate. So it'll be 100 times the mole fraction. So the total flow rate of the pentane that's in the stream is just 100 times 0.00304, which is 0.304. For oxygen, we'll have to take x1 times 100. And we're going to represent, though, this by the variable N4 instead of writing it out as x1 times 100. We could calculate the flow rate of nitrogen by taking this 0.895 minus x1 times 100. But instead, what we're going to do is we're going to say that the flow rate of this nitrogen is equal to the total flow, 100, minus all the flows of all the other components, since all 4 of these have to add up to 100. So before writing this down, let's go ahead and calculate the flow rate of CO2 in the stream. The flow rate of CO2 is going to be equal to the fraction of the stream, which is CO2, 0.102 times 100. That gives us 10.2. So outside of the nitrogen, the sum of the flow rates of the other 3 components is just going to be 0.304 plus N4 plus 10.2. We're going to subtract that sum from 100 in order to get the flow rate of nitrogen. The result is shown here. It's just 89.5 minus N4. So it's pretty clear that if we subtract from 100 N4, we have a minus N4 here. This number here comes from taking 100 minus 10.2 minus 0.304. If you want, you can verify this using a calculator. Now, what I'd like for you to do is take a moment and then perform the atomic balances for this reactor. And then I want you to also perform an inert molecular species balance. We will use the atomic balances for the species that we'll use the atomic balances to do our mass balances, but in addition to that, and we'll include in that atomic balances those reactive species, but in addition to those atomic balances, we can do inert molecular species balance. So I hope that you'll take the time now to pause this lecture and write down those balances, because in a moment we're going to move on to the next slide where the results are shown. Well, here are the results. I do hope you took a moment to try to do this yourself before moving on. What I'd like to do is go through each of the balances, how we obtain them, and then from those balances solve for the unknowns that we have here. So we're going to start off with the atomic balances for carbon. That's the very first line right here. What we're going to say is the carbon atoms that come in is going to be equal to the carbon atoms that come out. So to determine how much carbon comes in, we're going to look at each of the streams that come in and determine the carbon flow rate in those streams. So this first stream here, we see that this is pure pentane, and this pentane has 5 carbon atoms. If you look at the formula right here in the reaction, each pentane molecule has 5 carbon atoms. So we're going to take 5 times the flow rate of pentane in order to calculate the carbon that comes in. So we're going to take 5 times N1. The air has no carbon in it, so there'll be no contribution to carbon coming in from this stream. So the total is just going to be 5N1. We're going to set that equal to the carbon that comes out. So let's look at the streams over here that come out. The first one up here is water. It has no carbon in it, so there's no contribution from that. Now let's look at the dry gas. The dry gas, we do have some pentane. So the flow rate of pentane we determined is 0.304. We'll multiply that by 5 to account for the fact that there are 5 carbons per pentane. So we have 5 times 0.304 on the right-hand side of the carbon balance. And we're going to add to it the carbon flow of the other associated with all the other components. There's no carbon in the oxygen, so there's no contribution from it. There's no carbon in the nitrogen, so no contribution from it. CO2 does have carbon. There's 1 carbon atom in each CO2 molecule. So we have 1, which is not shown here, but there's a 1 times the flow rate of CO2, which is 10.2. So this completes our carbon balance. If we can solve this very easily for N1. We can find that N1 is 2.34. So we've got one unknown solved for. Let's move on. Let's look at the hydrogen balance. We're going to repeat the process again. We're going to look at the hydrogen that comes in each of the streams over on the left-hand side here. So if we look at the top stream here, the pentane, there's 12 hydrogen atoms per pentane molecules. We'll have 12 times the flow rate of pentane, which is N1. I wrote N1 down here. We know it's 2.34, so we can just plug that in just a moment. If you look at this, the air stream coming in, there's no hydrogen in the air stream. There's no hydrogen in the oxygen nor the nitrogen. So there's only the 1 contribution to hydrogen coming in from the pentane. We're going to set that equal to the hydrogen that comes out in the product stream. And let's start with the top stream here, the water. There is hydrogen in the water. There are 2 hydrogen atoms per water molecule. So we're going to take 2 times the flow rate of water, which is N3. And they're going to add to it the hydrogen flow associated with the components in the dry gas. If you look at this dry gas stream, there's hydrogen only in the pentane. So we'll take the flow rate of pentane, 0.304, and multiply that by 12 because there's 12 hydrogen atoms per molecule. So we'll add to this 12 times 0.304. Since we know N1 is 2.34, we can solve this for N3. We find that N3 is 12.2. We have 1 atom balance left, and that's oxygen. We're going to be repeating the process once again. We're going to go through all the streams that come in and account for the oxygen flow associated with each of those species and set that equal to the oxygen out. So start off with the pentane here, the top stream. There's no oxygen in the pentane, so we don't have to include any contribution from it. There is oxygen flow in the air stream due to the oxygen there. There are 2 oxygen atoms per oxygen molecule. So we're going to take 2 times the flow rate of oxygen, which according to our process flow diagram is 0.21 times N2. That's all that comes in. We're going to set that equal to what comes out. So we look over here, the top stream, the water comes out. There is 1 oxygen atom per water molecule. So we're going to have 1 times the water flow rate, which we said was N3. We do know N3 is 12.2. I'm not going to plug that in right now, but we do know N3 is 12.2. So let's add to it any oxygen flow that's associated with the dry gas here. There's no oxygen associated with the pentane. There is oxygen associated with the oxygen molecule. So we're going to take 2, since there are 2 oxygen atoms per oxygen molecule, times the flow rate of that oxygen stream, which is N4. And then we're going to add to it the oxygen flow associated with CO2 because we don't have to worry about the nitrogen. We'll just move on to the CO2. We know there's 2 oxygen atoms per molecule of CO2, so we're going to take 2 times the CO2 flow rate. So we have 2 times 10.2. Look in this equation here. We know N3, and we have calculated that we don't know N4, which is what we're going to solve for. Unfortunately, we don't know N2. So all we can do is simply plug in for N2 over here. And if we simplify this equation, what we end up with is that we can rewrite this such that N4 is equal to 0.21 over here on the far right-hand side. N4 is equal to 0.21 times N2 minus 16.3. That's just this equation rearranged to write in terms of N4 equals to something. We could have written it as N2 equals to something, but I'm thinking ahead to the nitrogen balance, and with the nitrogen balance, it makes it a little bit easier if we solve this for N4 is equal to something. So now let's look at the inert balance. We're going to say what the inert flow rate coming in is equal to inert flow rate coming out. This is a molecular balance, so we don't have to worry about atoms. We're just going to say that the moles of the nitrogen molecules coming in is equal to what comes out. There's only one place nitrogen comes in. That's in the air feed here. So we're going to take 0.79 times N2. That's what comes in. I'm going to set that equal to what comes out. There's no nitrogen that comes out in the water. And in this stream right here, we know the nitrogen that comes out, according to our process flow diagram over here, is 89.5 minus N4. We can rearrange this to solve for N4. N4 is just 89.5 minus 0.79 times N2. Now we can take these two equations and set them equal to each other to solve for N2. We have these two equations and two unknowns. This is the first equation that involves N2 and N4, and this is the second equation that involves N2 and N4, and they're easy to solve together because we have written them as N4 equals to something in both cases. So if we set those two equal, we find that N2 is equal to 105.8, and we can solve for N4. In this case, we're solving for N4 from the nitrogen balance right here. We're plugging in N2 into this equation. We find that N4 is 5.92. Next, what I'd like for you to do is take a moment and see if you can calculate the theoretical error and the excess error. And where the excess error is given by 100 times the moles fed minus the moles theoretical over the moles theoretical. Take a moment, see if you can do that before we move on, and I'll show you how it's done. Okay, hope you took a moment to do that. The theoretical error we can calculate by taking the moles of pentane that have been fed, which is 2.34, and then multiplying it by the ratio of the stoichiometric coefficients in the combustion reaction for oxygen and for pentane. So we're going to take 2.34 and multiply by the coefficient for oxygen, which is 8, divided by the coefficient for pentane, which is 1. So what we're doing is just multiplying by 8. We need 8 oxygen molecules per pentane molecule, so we need 18.72 moles of oxygen per mole, or 18.72 moles of oxygen to be fed to this process to provide the theoretical oxygen. The theoretical error we can calculate by taking the flow rate of oxygen and then multiplying that. There's 100 total moles of air per 21 moles of oxygen. So oxygen is 21, or air is 21% oxygen. So if we take the ratio of 100 to 21 and multiply that by 18.72, that will give us the total airflow, which is 89.1. You can think of this that if we take 0.21 times this number, it has to be equal to the theoretical oxygen. So essentially what we did is just divide by 0.21 here in this equation. You can verify that for yourself. The percent air excess we said was 100 times the actual amount that was fed. The actual amount of air that was fed is 105.8. Subtract off the theoretical, take that quantity, divide by the theoretical, and we end up calculating that it's 18.7% excess. Next, I'd like for you to calculate the fractional conversion of the pentane. I'd like for you to take a moment to do that before proceeding. So why don't you pause this and try it. Well, as always, I hope you try to do this on your own before moving on. The percent conversion is just going to be given 100 times the moles of pentane that were fed minus the moles that leave, which gives us the moles that reacted, and we'll divide that by the moles that were fed. This is a pretty small number, so we expect the conversion to be pretty close to 100%. If we take the moles fed minus the moles that leave, which gives us the moles reacted, divide that by the moles fed, times 100, we get 87.0%. The problem we're going to work in class is described here. Now, this problem is a combustion problem just like the other one, except we're not. We're given information about the organic hydrocarbon that we're burning in terms of a volumetric flow rate. We're going to have to convert that volumetric flow rate to a molar flow rate in order to do our balances around the combustor. I want you to think about how you do that. You can go back and review some of the work we've done, some lectures before. It's not too hard. I think you should be able to do this pretty easily. You're going to have to know the density of methanol, which you can look up online. And you're also going to have to know the molecular weight of methanol, which you can also look up online. But once you look those up, you should be able to convert this liquid flow rate of methanol to a molar flow rate, and then label a process flow diagram with the information that's shown here, and then actually solve the problem. Now, if you go ahead and do this, it'll help you, I think, be prepared, or try to do this. It'll help you be prepared for class. And next time we're going to do is we're going to continue our discussion of combustion reactions and work a couple more problems. Bye for now.